Okay, so today we're going to talk about limiting reactants. Stoichiometry part 2. The limiting reactant. Limiting reactant. So just based on the words there, you can probably guess what this is. A limiting reactant is the reagent. Reagent and reactant are synonyms. That is depleted first causing the reaction to halt before all reactants are consumed. Does that make sense? We're gonna look at some examples. Let's find a picture because I like to be pretty sometimes. Would you chill? Would you chill? Oh boy, not Chemica. Yeah, let's throw that one in there. That looks sciencey. Look, there's a picture of some beakers. We're doing science. Why are we awing?
Or what, Tiffany?
It's a cute picture of chemicals. I've never heard that before. I love that whenever someone, like some stock image company, wants to make a sciencey looking image, they just grab some beakers and some flasks and put water with some coloring in them and like maybe a stirring rod. Yeah, dude in a lab coat. That's obligatory.
What did he do with our lab? It was water, flasks, and a lab coat.
Yeah, with calcium, with copper chloride.
That's too specific.
It was blue. It looked like Kool-Aid. It's true.
Ooh, that sounds good. It does.
Well, thankfully none of you drank it.
Wait, what?
When we did the lab, dude. Were you not here?
He wasn't. He just didn't pay attention. Is that supposed to say first or first?
Fine. First. Okay. Questions on what a limiting reactant is?
No, yes, I'm still on first.
Okay, just right.
Yeah, you wrote
Right.
it.
Right. Guys, I'm pretty hyped. On Friday, I have a tattoo appointment. I'm going to add on to my sleeve on my arm. It's, oh no. Trinity has said like 3 words to me the whole year, and now she's like, I found that guy's TikTok. Wait. Did it just show up on your For You page?
Yeah.
Man, that's what's crazy. That's what's crazy. When babies, yeah. That video has 3 million views now, which is crazy. What? I guess. What, Miguel?
So we have that liquid. What? How would it make a sun? That's what I'm confused.
The copper chloride? Okay, so it would bond to certain receptors in your cells, making it so that they couldn't metabolize glucose anymore, and you would die. You have like a sick feeling. All right, let's keep on going. So limiting reactant. Okay, so let's just do our classic example of a reaction. Let's do good old methane O2. I'm gonna screw this up, but so far this is looking pretty neat. C O 2. Do I have enough room? H 2 O. Beautiful. Oh my gosh, I'm so proud of myself. All right. Thank you, lady. All right. So this is a reaction that we've talked about a lot, and I know you're sick of seeing it, but it's one of my favorites. Okay, CH4 plus O2 makes CO2 and H2O. If I just had myself a little can of methane, a little natural gas container, right? Say I'm going camping for the weekend and I want a little camp stove. Okay, so I get a little tank of methane, and I can attach a little burner to it and light the burner, right? Well, if I go out to the woods and I'm cooking on my camp stove, you know what? While I'm doing this, I'm gonna draw. I'm cooking on my camp stove. Fire. It'd be spiky fire. Oh yeah. See, I'm adding details. Look how beautiful. Okay, we got our. This looks like the Olympic torch now, and it's got a valve on it. Valve, and then we got our tank of methane down here, and it's like CH4. So all the methane is in the tank, yeah? Where is the oxygen in this reaction? It's in the atmosphere, yes? It's what we breathe, right? So in this reaction, let's say that this canister has 2 kilograms of methane. There's G. Okay, 2 kilograms of methane. And I'm reacting it with oxygen in the atmosphere. And the atmosphere weighs something like, this is just a total guess, like 1.4 times 10 to like 28 kilograms. No, it's not that much. It's like 19. Yeah, times 10 to the 19th, something like that. Times 10 to the 19th kilograms of O2 out here. So in this reaction, which of these two is going to be the limiting reactant? The methane, right? Because we have a literal Earth's atmosphere worth of oxygen. We're not going to run out of oxygen before we run out of methane, unless I have like a cheat code that's unlimited methane. Maybe. Okay, so for instance, if I was to seal off a small container, right? So when you're burning a candle, you're going to run out of candle wax before you run out of oxygen, yes? Right? Well, what if you put the lid of your candle onto the candle? It stops burning because the oxygen is all depleted. When you contain the oxygen just inside that little area in the top portion of the candle, it stops burning because the oxygen becomes the limiting factor, becomes the limiting reactant. Oh, it's 5 times 10 to the 18th. Hey, I was like relatively close, right? That's the weight of the atmosphere. Because Vince is a fantastic student, he looked up the actual weight of the atmosphere. It's 5.4 times 10 to the 18th. 5.8? I don't remember. Anyway. So do you see how that is? So the the CO2, oh, it's not CO2. The CO2 and the H2O is being produced, but the CH4 is the limiting reactant. Okay? All right. So the way that we do this is you're going to be given an equation, just like, you know, always. And you are going to be told the amount of stuff in that equation. So for instance, let's look at this reaction. This reaction is LiOH, which is lithium hydroxide, combined with carbon dioxide, makes lithium carbonate, Li2, CO3, and water. I don't know if people are like furiously taking notes or playing nitro type. It's always really like kind of a moment of stress for me. I hear tappity tappity clickety click. Yeah.
I'm typing out.
Okay. Lithium hydroxide combined with carbon dioxide makes lithium carbonate and water. Okay? So we need to figure out the limiting reactant, but first we need to be told how much there is of stuff. Okay? So let's say that we have in this reaction let's say we have 12 kilograms of lithium hydroxide. And we have 48 kilograms of carbon dioxide. Okay. What is the limiting reactant? Limiting reactant. I can't spell react. Nope, still wrong. There we go. Okay. What? Wait, what? Thanks, Brendan. All right. How are we going to do this? You can probably guess the first step. Yeah? Vince, what's going to be the first step? Okay. Balance the equation. If you have not learned how to balance the equations yet, please come talk to me. That's a very, 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 very important step. Okay? So how are we going to balance? Well, I'll do it really quick for you. It's super easy. Done. Ashley? Sure. Were you bracing yourself for me to like berate you?
Yeah.
Mm.
I did my notes too.
Later. You shall be berated later. All right. Okay, so we need to balance the equation. Well, that's done. Cha-ching. Okay. That's actually a pretty decent little check mark there. Pat myself on the back when I can. All right. What should we do now? What do you think? Anybody? Anybody? Anybody?
It was Molar Mass. Molar ratio. Molar ratio balanced it. 2 to 1 to 1 to 1.
So 2 to 1 to 1 to 1. 2, 1, 1, 1. To check. Okay. Now what? You're on the right track there, Leighton.
Molar Mass.
Molar Mass. Molar Mass. So what's the molar mass going to be of these things? So how do we do this again? Franklin? How do we determine the molar mass?
Molar mass. You basically just like, well, you look up like the mass of those
Yep. Yep. So for those of you that could not hear, Franklin said we need to look at the mass of each atom in the molecule and add them all together. Yeah? Pretty simple. So what's lithium?
7.
7. Okay. 7. Oh, that's not a plus. What is oxygen? 16. What's hydrogen?
1.
This equals?
Is hydrogen like uses the base or naturally one?
What?
24.
Well, remember, hydrogen is just one proton. So, and each proton has a mass of 1 AMU. Okay. So 24 is lithium hydroxide. And what's CO2? So carbon is what? 12.
12
What's oxygen?
plus 16. No, plus 16 times 2, which is 30.
16. And there are 2 of those.
32.
So that gives us the mass of what?
44.
And what is our units?
G per mole.
Grams per mole. Good, Leighton. Okay. Are we clear on how we determine molar mass? Pretty straightforward, yeah? We just add the atoms together. That gives us the weight of the molecule, and we can just simply put grams per mole on it. Perfect. Okay. 4. And I think this is where a lot of people start getting lost. We need to determine the number of moles in the reaction. Okay? So we're going to take this here. Oh no, that's not what I want. I just wanted the one thing. Can I do that? Nope, apparently I can't do that. All right, whatever. The number of moles of the reaction. So we have 12 kilograms of lithium hydroxide. How many grams is 12 kilograms? Promise this is easy. 12,000 Remember, a kilogram is 1,000 grams. 12,000 grams lithium hydroxide. And we divide that by the number of grams per mole. We divide that by the molar mass to determine the number of moles. Yes? Yes, Mr. Croshaw.
Yeah.
All right. So 12,000 grams divided by 24, which is lithium hydroxide's mass, right? Molar mass. If you want to do this along with me, I would recommend grabbing a calculator. Because I don't know about you, I can't get 12,000 divided by 24 easily in my head. Oh my gosh. That is really, that's a really nice number. That was not planned. Yeah, 12,000 divided by 24 is 500. Wow, I guess I actually could have gotten that pretty easily in my head. That's really interesting. Grams per mole. So what happens is the grams cancel each other out, right? And we end up with 500, no, not 550, 500 moles. Cool, of lithium hydroxide. Okay, now we need to do the same thing with carbon dioxide. We have 48 kilograms of carbon dioxide, which is equal to how many grams?
Wait, how many? 48?
48.
48,000.
48,000 grams of carbon dioxide divided by how many, what's the molar mass of carbon dioxide? 44 grams per mole. 48,000 divided by 44. That means that we have 1,090.9 moles of carbon dioxide. Okay? That's not as nice of a number. You're right. Now, our fifth step is going to be use mole ratio to determine well, you're just really going to use the mole ratio, okay? Ratio. Or use is kind of a weird word. How about apply? How about apply? Apply mole ratio? Yeah, that sounds better.
Sounds smarter.
More scientific, yes. Apply the mole ratio. So what is our mole ratio? Well, it's written up there, right? 2 to 1 to 1 to 1. Right now, we're only worrying about the reactants. So it's 2 to 1. So how many moles of lithium and how many moles of carbon dioxide do we need for this reaction to happen? How many moles of lithium hydroxide and how many moles of carbon dioxide do we need for this reaction to happen?
I don't know.
What, Vince? Carbon dioxide. The mole ratio tells us we need twice as many lithium hydroxides as we have carbon dioxides. Yes? Because it's 2 to 1. In our recipe for making cookies here, we need twice as much flour as we have sugar. Do we see how that works? The mole ratio is just a recipe. We need twice as many lithium hydroxides as we have carbon dioxides. Okay? So we applied the mole ratio. We need twice as much LiOH. Okay? Do we have twice as much LiOH? The number of moles. How many moles of LiOH do we have? 500. How many moles of carbon dioxide do we have? 1,090. Which of these two reactants is the limiting reactant? Which one of these is going to run out first? Guys, it's literally a 50% chance of being correct even if you just guess. Throw it out there. The lithium hydroxide, because it's going to run out first, right? We only have 500 moles of this. We have 1,000 moles of this. If we had 500 moles of lithium hydroxide, we're only going to be able to react 250 moles of carbon dioxide. Do you see how that works? We are only going to be able to react 250 moles of carbon dioxide because it takes 2 of these for every 1 of these, and we only have 500. Do we see how this works? More or less? Yes? Okay. So you might be asking yourself, well, why, or you probably ask yourself this a lot in this class, why in the world would anyone need to know this? I'll tell you why. Because this is a thing that you've probably seen before. This is the space shuttle. And on board the space shuttle, there were oftentimes these organisms called Homo sapiens. And Homo sapiens do this thing where they breathe out carbon dioxide. And carbon dioxide happens to be toxic to Homo sapiens. Okay? Well, if you and I were the people in charge of making sure that the astronauts didn't die on the space shuttle, and we only put 12 kilograms of lithium hydroxide on the space shuttle, you and I would be fired because we would have killed 6 astronauts. Because on the space shuttle, they used lithium hydroxide canisters to purify the air, to pull the carbon dioxide out of the air. And then as an added bonus, they got drinking water out of it. Pretty crazy. So you can take the carbon dioxide that people on the space shuttle were breathing out, and you can pull water out of it. Not the water that they're breathing out, just the carbon dioxide, reacting it with lithium hydroxide. Okay? So, lithium hydroxide was used on the space shuttle. They needed to know for sure that the carbon dioxide was going to be the limiting reactant. Why? Because you want to make sure that there is enough lithium hydroxide to react with the carbon so that the astronauts don't die. Okay? We have less time than I would like to have. I'm going to end the class there, or the video there. On the assignment that I have assigned to you today, there is a video that will be helpful as well. I know that we only really went through one, well, we went through a couple of problems really. We went through a couple of examples rather, with the with the methane, right? There's an assignment called limiting reactants on Canvas. Get to it. This is where I'm going to end the video.